Good morning students. Today we will discuss a very important concept, in fact two concepts, which basically a connection between entropy and probability, and this is the first time I will in this course derive from first principles the connection between entropy and probability. After deriving this connection, I will show why nature prefers to order particles at equilibrium to have a velocity distribution which is normal or Maxwell-Boltzmann. So, you know that if you look at a system which is isolated and has been given sufficient amount of time to evolve, the velocity distributions, for example, for particles in this room will be normally distributed. Also, for example, if you have energy levels of for atoms at a given temperature and you ask yourself a question, how are these energy levels distributed, or how are the particles distributed in energy levels, then the distribution turns out to be Maxwell-Boltzmann like. Why is it always Maxwell-Boltzmann for systems at equilibrium? And the answer lies in entropy maximization. We shall see in the lecture that there are these distributions, the only distribution which maximizes entropy are the Maxwell-Boltzmann distribution. So, we will derive this formally, and that is going to be the second half of this lecture. So, I will start with so I will write down the basically the focus of our present lecture. So, I am going to talk about entropy and probability, and here I am going to the first task is to derive a connection between entropy and probability. So, I will show that entropy is a function of probability. Okay. So, this is the connection, and in the second task towards the second half of the lecture, I will show why why nature prefers Maxwell-Boltzmann distributions at equilibrium. Okay. For example, why is the distribution of velocities, let us say if you have a one dimensional gas at equilibrium, thermal equilibrium T is always to some normalization constant always e raised to minus mv square over kBT. Okay. Why not something like e raised to minus some alpha times v exponential. Okay. So, all these distributions you can take some v to the power n and so on and so forth. All these distributions are rejected, and what is selected is a normal distribution at equilibrium. Okay. So, the reason why this distribution is selected over other distribution is because a Gaussian distribution is a distribution of maximum entropy. Okay. So, we shall systematically derive this distribution by maximizing entropy. So, that is the agenda of our lecture. So, we will start off with a simple Boltzmann's definition of entropy. Remember, the task is to connect entropy with probability. So, We will start off with the definition of entropy given by Boltzmann. So, Boltzmann gave us the prescription of entropy, that it is logarithmically related to the number of accessible states. So, this is the famous connection between number of states and the entropy for any system given by Boltzmann. Okay. Now, why not we take, why didn't Boltzmann take something like e raised to omega or s going as some omega to the power n? Well, there is a reason why Boltzmann did not take choices like e to the power omega or n omega to the power n, for the simple reason that he wanted entropy to be additive. Or extensive, and we shall see why logarithmic dependence on number of states makes entropy naturally extensive. Now, suppose you take a system and call it let us say you have two systems A and B. Our system A can exist in, let us say, omega A number of states. Okay. So, number of states for our system A is omega A. I am going to write it outside so that the figure does not become busy. So, this system has these many states, and let us assume that the system B has access to omega B states. These are the number of states. Okay. So, one can say that the entropy of system A is like ln of omega A, the natural log of omega A, and similarly entropy of system B is like ln of omega B. Fine. So, one would ask a natural question, what is the joint entropy or total entropy of the joint system, and I am called the joint system as A plus B. Okay. So, this would be definitely, this would certainly go as ln of, I am dropping the constant prefactors. Okay. The Boltzmann constant has been dropped, we have taken Boltzmann constant to be 1. So, you can take it as ln of omega A plus ln of omega B. Okay. And then you can write it as ln of omega A times ln of omega B. So, I am basically writing down the entropy to be additive, because that is what I want. It should be an extensive quantity, it should scale with system size. So, if I double up the system, the entropy is expected to double up, and so I have simply added the two entropies. What it has given me is a logarithm of a product of the number of states in each of the system, and this is precisely nothing but, if I call it as ln of omega total, where omega total is the total number of states accessible to the joint system. So, if you have first system existing in 5 states and the next system existing in 6 states, a joint system would definitely exist in 30 different states, which is precisely what is written here. So, hence you expect S to be logarithmically related to the number of states accessible to a system. So, any other combination, any other mathematical formulation for entropy and total states will not lead to additivity. Okay. So, this is the nice this is the reason why Boltzmann has taken entropy to be logarithmic related to number of states. It makes entropy naturally additive. Okay. So I will write down the conclusion. This is the reason why you take entropy to be logarithmically dependent on the number of states. Now, like I said, we are chasing a connection between entropy and probability. Okay, this is the next task. So I have just derived, I have not derived, I have just explained why entropy is logarithmically related to number of states. Now I am going to develop a connection between probability and entropy. Okay, so I know that entropy is a measure of disorder. So the relationship that I am going to chase between entropy and probability has to respect that that physical meaning of entropy. And so by disorder I mean higher access to number of states, okay, or access to a higher number of states, a larger number of states. So certainly if you go into a classroom and you are 5 students, let us say, and you go to a classroom and you see 5 benches, and the benches are wide enough to accommodate only one student. What you will do is you will basically go and sit in each one of the benches and all benches will be occupied. So 5 benches, 5 students, each one sitting in one bench, because a bench can accommodate only one student. If a professor walks in, he says that okay, 5 benches and 5 students, it is an ordered system, okay. But imagine these 5 students went into a class which had 50 benches. Now they can sit anywhere, they could sit together or they could sit far away from each other. So if now somebody walks into the class, they may see a certain configuration where the students are all sitting at random locations in 50 benches, 5 of them sitting at random locations. So naturally the second configuration is more disordered than the first configuration, and here the disorder simply arose because you gave more number of states to these 5 students to sit. If you had given them less number of states, they would have been more ordered, like the first case. So clearly disorder can be in some sense connected to total number of states available. So increase the number of states, you increase possibility of disorder, okay. So I am going to take the example of dice, okay. So we all know a dice is has 6 faces. So let us say you have a unbiased dice, okay, like a dice is like a cube having 6 faces, okay, and let us say that you take n such dice, okay. So you have taken n such dice. So you take the first dice and you take the second one and you take the nth one, okay, first, second and nth, and you roll them. roll all of them. Okay. So, the first dice may show let us say it may show, I am going to write only the outcomes here. So, the first dice may show an outcome, let us say 6, the second die may show an outcome 5, the third die may show again an outcome 6, so on, and the last die may show, let us say, an outcome of 1. These are the outcomes. Okay. So, is the experiment clear to you? You have taken n dice and you have rolled all of them. So, the first die gave you 6, the second die gave you 5, the third die gave you 6, the fourth die gave you 4, and the last die gave you 1. So, it is like what I have written in front of you here is one state of the n dice system. Okay. So, this is so these are the outcomes. So, I will call this as one possible state of the n dice system. This is one possible state. So, if you want to classify this state, okay, you can classify this state, this one state, as you can call this as a micro state. So, you can say that this one state can be classified as, you can count the number of 6 that you had, or count the number of 1s, count the number of 2s, count the number of 3s, and up to count the number of 6. So, you can say how many dice give you the outcome 1. So, that is n 1. Let us say you had you had take some number, you had 7 dice that gave you 1, and how many dice gave you the outcome 2? Let us say you had 11, and all the way you count the number of dice that gave you the outcome 6, let us say it is 19. Okay. And we know that summation over all the different phases, some of these ni's should be the total number of dice, okay, which is the total number of So, what we have done is we have rolled n dice together and we have simply counted how many dice gave you the outcome 1. 7 of them gave us the outcome 1, and we counted how many dice gave us the outcome 2. 11 of them gave us the outcome 2, and finally, since the die has only 6 phases, we do this calculation up to 6. So, number of dice that gave the outcome 6 were 19, and I know the total number of dice that we tossed was big N. So, summation Ni has to be the big N. Okay. But there are many ways in which I can keep these values of Ni's. So, I can change my microstate, okay, such that the first die gave me 4, the second die gave me 3, the third die gave me 6, and so on, and the last guy gave me 5, such that I still have n 1 as 7, n 2 as 11, and so on, the same macro state. So, it is possible to have many different types of orderings that correspond to the macro state that I have taken. Okay. A very a simple example would be take a coin toss, for example. So, if I take if I take 4 coins and I say that number of heads So, I take let us say 4 coins. So, n equals to 4, and I say that number of heads are 2 and number of tails are 2, such that nh plus nt is 4. How many ways can you have it? Well, you can have let me just write down a few ways, and you should be able to tell us naturally. So, you can take a head here and a head here and a tail here and a tail here, or you can take a head here and a tail here, a tail here or a head here. So, all these configurations belong to nh equals to 2, nt equals to 2. 2 plus 2 is 4, which is the total number of coins that I have tossed, and the answer is clear. You know the total number of states that are accessible to you is NC2. So, you can take 4 factorial by 2 factorial into 2 factorial. So, this is basically 6 ways. So, you have 6 microstates that are possible, or I will write down instead of ways 6 microstates. Okay. So, that was a simple example from a coin. Let us go back to our example of the dice. So, like I said, if I have tossed the die n dice together and I have simply counted how many times I got the outcome 1 and how many times I got the how many dice gave me the outcome 2 and how many dice gave me the outcome 6. So, basically I have these numbers n1, n2, n3, n4, n5 and n6, because there are only 6 faces, and I know that summation I going from 1 to 6 ni is equal to the total number of dice. That were tossed together. Okay. So, if I want to know how many states these n dice can stay together with the specified values of these small n1, n2 all the way up to n6, then this is nothing but factorial n being the total number of dice divided by a product of these ni's. Okay. Okay. Now, if n is large, okay, then I can approximate n factorial then I can approximate n factorial as n by e to the power n. This is called as a Stirling approximation. Okay. So, you may actually have a better approximation of Stirling. You may take n by e to the power n into square root of 2 pi n. This is better, but for the purpose, so both will give you the same result. I am going to choose this one. Okay. Slightly lesser accurate, but it suffices. So, I know that my n factorial is very large. So, I can approximate it as a Stirling approximation, and this will give me n by e to the power n. The denominators are also, you know, all these small ni's are also large. So, I will approximate these also by Stirling's formula. So, I am going to write it as ni by e to the power ni, and then I am going to take logarithm on both sides. Okay. So, we are now taking logarithm on both sides. What you will see is basically and I know that this is nothing but entropy over Kb from the Boltzmann's prescription. So, if I take the logarithm of n, the expression splits up into two logs, and the denominator becomes summation over I okay. And you can write now this as S over Kb. Now, it is just a matter of simplifying things, and log e to the base e is taken as 1. So, this is nothing but n log n minus n, that is the first term, okay, minus summation I going from 1 to 6. I am going to write it as ni log ln ni minus ni, okay. And what you can see, so this entire thing is summed over I, and since I know that summation over all ni's is my total number of dies. So, basically this term cancels with this term. So, there is a summation outside the bracket, and what I have is basically n log n minus summation I going from 1 to 6 ni log ln ni, okay, because summation ni is big N, right. So, I need to simplify this further, which is very simple. What I will do here is basically divide this by n and multiply this by n, okay. So, let us see what this gives us. This will give us ni log ni by n plus ni log n, fine. And we know that so this is the birth of or appearance of probability. We know that number of times the ith outcome came divided by the total number of dies is nothing but the probability of getting the ith outcome, okay. So, I am just going to rewrite the previous expression as minus summation I going from 1 to 6 ni ln pi, and the second expression is simply minus I am just going to split the summation into two summations. Okay. Now, look at the first term and the third term. This is a constant ln n, okay, and summation I going from 1 to 6 ni is nothing but n, okay. So, you can knock off the first term and the third term, and what you are left with is just minus summation 1 going I going from 1 to 6 Ni ln Pi. Now, we are just one step far away from our final expression. So, what I am going to do is multiply by n and divide by n. So, I add a minus n here. So, I have multiplied the entire thing by n and I have divided each term in the summation by n, same thing. The entire thing has been multiplied by n and the entire thing is nothing but sum of n terms or 6 terms. So, I divide each term by n. So, this is nothing but minus n summation I going from 1 to 6 Pi ln Pi. Since we have this condition of probability, the probability is defined as Ni over n. Okay. So, now we have this connection. So, the left hand side was S over Kb as minus n summation I going from 1 to 6 Pi ln Pi. Now, this is derived for a dice where each die can have 6 possible outcomes, but in general you can do it for any system where the number of states accessible to each particle is n. So, this is the definition of so I could in principle take a t phase die. Instead of taking 6, I could have taken a t phase die and taken the sum up to t. Okay. So, t was 6 in this case. In principle it could be any number. Okay. So, this is also called sometimes the Shannon's form of entropy. That is a beautiful relationship between probability and entropy. Okay. So, this is the connection between probability and entropy. Now, we were focusing on our second agenda was to basically maximize the entropy and as a function of probability and find out which probability density is the maximum of the entropy. So, the next topic is the entropy maximization or maximum entropy principle. Okay. So, you can name it whatever you want to. The agenda is nothing but find distributions, probability distribution that maximize entropy. Now, this is a subject of optimization under a constraint. I am optimizing something, I am optimizing entropy under certain constraint, and I will basically highlight what is meant by these constraints. Okay. So, basically mathematically this is a problem of optimization. So, I am going to basically take an example and explain this point. Okay. So, instead of directly optimizing entropy, I will take a random function. Let us say I have a function f of two variables x and y. Okay. And is some function, and I want to maximize f under a constraint that some g of x y equals to 0. This is my constraint. Okay. So, this is where you can use the method of Lagrange multipliers. Okay. So, let me demonstrate this method. So, the method of Lagrange multipliers simply states that you construct a Lagrangian, okay, some sort of a Lagrangian, let us say that this is L. This is written as our function f minus lambda, which turns out to be a Lagrange multiplier, into g, which is our constraint. Okay. So, this is the Lagrange multiplier, and I am going to maximize my S L, my Lagrangian. Okay. I will take one very cute example. So, what you do is basically you say that I will take derivative, since L is extremized, I am going to take derivative with respect to x, and this will be del f by del x minus lambda times del g by del x, and I am going to take derivative of L with respect to y and get del f by del y minus lambda times del g by del y, and naturally I can also take derivative with respect to lambda, which in this case will just give me L g, which is 0, and that is my constraint. Okay. The derivatives with respect to x and y are also 0, because that is the condition for maximization of L. Okay. So, these derivatives, so the values of x and y that give me these derivatives as 0 are the values that maximize f. Okay. Let us take a simple example. So, if I ask you, if you take a circle okay. So, let this be a circle of some radius c. So, the equation of circle is a square plus y square equals to c square, and I ask you a simple question. Let us say the circle is centered at the origin, and I ask you a simple question. What is the point on the circle where x plus y becomes maximum? Okay. So, the question is very clear. Stated mathematically, this means that I have a function x plus y that I want to maximize subject to the constraint my constraint is g of x y, which is equal to x square plus y square minus c square equals to 0. Okay. So, basically this problem means you have to maximize this function x plus y on the circle. So, the constraint is that x square plus y square minus c square is 0, which is my g of x y, and I can use the Lagrange multiplier methods. So, I will say that this is my Lagrangian as I defined earlier, f minus lambda times g. Okay. So, now you can write it as x plus y, our function, minus lambda times x square plus y square minus c square. Okay. Take the derivatives with respect to x, and this will give you 1 minus twice x into lambda. Take the derivative with respect to y, these are partial derivatives. So, you will get again 1 minus twice y lambda, and the third equation basically is del L by del lambda, which is nothing but our constraint x square plus y square minus c square equals to 0. Okay. So, you have to solve these three equations, and the x y that you get are the values of x and y where the function x plus y is maximum. Okay, because I already said that at these values of x and y, my Lagrangian is extremized because you have set the derivatives to 0. So, from here you can easily say that my x should be 1 upon 2 lambda, and from here you can say that my y should be 1 upon 2 lambda. Okay. And from here you can find out the values of lambda in terms of c. So, you can substitute 1 upon 4 lambda square plus 1 upon 4 lambda square minus c square equals to 0, and that will give you lambda as plus or minus square root of 1 by 2 into 1 by c. Okay. So, now you can see the answer. So, you can take if the circle was a unit radius circle, then c square would have been 1 for a unit circle, and you could have taken lambda as 1 upon square root 2, and that would have given you the point of maxima, you know, where x plus y is maximized as simply 1 upon square root 2 by 1 upon square root 2. If you put the values of lambda as 1 upon square root 2, you get these values. So, basically on a unit circle you would have been you would have maximized x plus y here at pi by 4. So, this was the x axis, this was the y axis, this would have been 1 upon square root 2, this would have been 1 upon square root 2, the sum of x plus y at x equals to 1 upon square root 2 and y equals to 1 upon square root 2 is the maximum, which is nothing but square root 2, okay, which is more than 1. So, if you had taken a point here, that would have given you x plus y as just 1. If you had taken a point here, your x plus y would have been 1, because there y is 1, x is 0. But if you take it here at theta equals to pi by 4, x plus y comes out to be square root 2, which is a maximum, right. So, let us extend this procedure to find out maximum entropy distributions. Okay. Now, this is the first time probably you are introduced to a rigorous derivation of the fact that if you leave something at equilibrium with certain constraints, the probability distribution is always Maxwell-Boltzmann like. Okay. So, you may want to pay attention to this derivation. So, I am going to take first an example of a discrete distribution where the outcomes are discrete, okay, like the coins or the dice. Okay. So, I am going to take systems of dice, coins, so on and so forth. So, you take for example, a T phased like before, you take a T phased dice, a dice which has T phases. Okay. And now you say that I know only one thing, that the sum of probabilities of each phase is unity. Okay. So, in some sense you have a constraint here, I call it as G of P I in fact as simply summation I going from 1 to 6 P I minus 1, right. So, we have a T phase die, so we are generalizing it, correct. Okay. You can take T to be 6, I am leaving it as a variable. So, this is my constraint, okay. And my function that I want to extremize or maximize is basically the entropy. So, my function of probabilities are nothing but the entropy, which is I know entropy over I will say I will take it as NKB, S upon NKB is the function that I want to maximize. It is nothing but minus of summation I going from 1 to T Pi ln Pi, okay. And here because this is a function of all the variables P1, P2 all the way up to P of T, I am going to say this is a entire set P of I. Right. This is a suppose the die was only 6 faces, this would have been a function of P1, P2, P3 all the way to P6. Okay. This means that this is a multi-valued so no, it is a multivariable function, both f and g. Now, if this is a constraint that the probabilities are normalized and you want to maximize your entropy. So, we are going to maximize S over NKB, which is our function. So, I am going to write it as before to be consistent. I am going to maximize my function which is nothing but S over NKB subject to the constraint and the constraint is G then I can use the Lagrange multiplier method. So, I can define a Lagrangian which is my function minus lambda, lambda being the Lagrange multiplier, f minus lambda times g, prescription remains the same. Okay. And you know that my variables are these are my variables on which my function is you know these are my variables. So, I take some variable p j. So, there are basically n equations, I will write only one of them. Okay. In like we had x and y, now I have p 1, p 2, p 3 up to p t. So, there are n equations here subject to the value of j that I pick up. This would be nothing but d over d p j of the entire right hand side. Okay. So, you plug the values here. So, f of p I is nothing but our function s upon n k b, and which I had taken as minus summation I going from 1 to t p I ln p I, and lambda times the function g was taken as summation I going from 1 to t p of I minus 1. Okay. That was my function g, fine. So, if you take the derivative with respect to p j, see only one term in this summation where p I is equal to p j will contribute. So, that is what I am going to take. So, this would be all other i's will go to the derivatives of all other terms where I is not equal to j will go to 0, only the term I equal to j will contribute here, and that will simply give me 1 plus ln p j, and here it will give me lambda times 1. Okay. And this is equal to 0, because this is derivative of the Lagrangian with respect to p j, that is our condition. Okay. Is p j is the maximum of our f, which is nothing but s over n k b. Okay. So, if you solve this for p j, what you get is basically 1 plus ln times p j, which gives you minus lambda. So, you can write this as p j equals to e raised to minus lambda minus 1. So, the left hand side depends on j, whereas the right hand side is a constant. So, what can you say about this? What can you say? You pick up any face of the die, its probability is the same. So, what can you talk? What can you tell about such a dice, which gives you same probability for all the faces? So, the dice is basically implies that it is an unbiased dice, each face has equal probability. So, the probability of the jth face comes out to be a constant. You pick up any j, first phase, second phase, third phase, fourth phase, tth phase, they are all the same, e raised to minus lambda minus 1. Lambda is a constant. So, the probability of any phase is a constant. So, this is an unbiased die. That is an important result. We are just going to normalize it. So, what I am going to do is normalize this probability okay, that is the only task. So, I can normalize probability by simply computing a norm which is nothing but summation over all values of Pj, and that is nothing but if I sum over all Pj's, what I get is simply t times e raised to minus lambda minus 1 okay, because each one of them is constant. So, the final normalized probability of a jth phase is the unnormalized probability divided by the norm, which is simply 1 upon t. This is your answer, and this you know. So, if you take a t equal to 6 phased die, then the probability of any phase, let us say a jth phase, would simply turn out to be 1 over 6. So, what we saw here is that if you leave the probability distribution without any constraint, apart from the fact that the probability distribution is normalized, if that is the only constraint you have, I am going to say this is the only constraint you have, then the PDF that you get is equal a priori distribution or unbiased distribution. Okay. Which means if I was to introduce a constraint, then the probability distribution would come out to be biased. Okay. So, the next lecture we will see how keeping constraints in the in your distribution will lead to probability distributions that are biased. Okay. So, we will carry out from here and meet in the next class and discuss things further.